Hello everyone. So far in this course we have talked about EVs and EV subsystems. We learnt about batteries, we learnt about chargers, motors, and what all things we need to learn as far as the parameters are concerned, performance of the subsystems are concerned, and also little bit about around the designing part of all these subsystems. Today we are going to touch upon analytics around these subsystems. Why do we require the analytics? What do we do in this analytics, and how do we go about doing that? So, if we go or talk about the analytics in electric vehicles and subsystems, we talked about various sectors in the whole ecosystem. We talked about batteries, chargers, vehicles, and the users who are finally the consumers of all these subsystems. And whenever we are talking about analytics, it means the first step is that we are able to monitor all these subsystems, capture the data, and then only that analytics would be performed on capturing on the captured data. So once we have the captured data, then there is a lot of things that we can do around that data and see that how the systems have been behaving, and is there a scope that we can improve the designs or the performance of the subsystem. So the basic purpose of analytics is threefold. One, we can figure out if there is any safety issue, if there is any threat, and can we take an action on that. So that is the first part of it. The second part is, can we do something on the predictions of these subsystems. So if we talk about, like we have been talking and studying about, that the battery is going to last for, let's say, 1000 cycles or 2000 cycles, from the data, from the monitored statistics, can I really tell and predict based upon the data that now 800 cycles are over and it is going to die in another 200 cycles, and what is the range? So if the initial battery was giving you 100 kilometers, what is the range that it is giving you now? It is 20 kilometers or 50 kilometers, so that there are no surprises. So how do we go about doing the predictions on that data based on the capturing of that information, and how what is the performance of that vehicle? So that is the second one. And the third, which may not be directly relevant to the users, but it is more relevant to the designers of these subsystems. So what is the feedback that you can give to your designers, to the OEMs of that manufacturing component or that subsystem? Can we do something about it? Is our data analytics good enough to figure out that there are faults in the design, and how can we improve the designs? So these are the three basic aims when we talk about analytics on that EV subsystem. So how do we go about doing it? The requirement that the first of us that we have is that we need to have the data from the subsystems. The second is that the systems to be analyzed need connectivity to the cloud, and here the biggest issue is that we are talking about the data to be captured from the mobile units. We are talking about vehicles after all. So when we talk about the vehicles after all, let's pick up one example, let's say batteries. So if we have to consider for the batteries, how do we capture that data? So we are saying that analytics could be done only if you have the data. Yeah, that is a basic requirement. Now how would we capture that data? The two ways of doing it, one is a direct way, another is an indirect way. When we talk about a direct way, this means that the batteries in itself should have a 2G or a 4G connectivity, such that while it is being used, you can capture that data, or it is being charged, it can capture or send the data to the cloud. So it is a direct connectivity that you need to have to the cloud. So that is the first way of doing it. That means the battery has inbuilt GPRS or a 4G module inside that, and is sending or relaying that data directly. In a battery, it can only do two functions. It is either charging or it is discharging, apart from lying ideal if we don't want to consider that case. So it is only two functions that a battery would perform. Either it would be charged or it would be discharged. So the second way that we talk about, that is an indirect method of capturing. If the battery does not have a 2G or a 4G module to keep on relaying that data to the cloud, the only way to capture that data is, one, while it is getting charged, the charger is connected to the cloud, right? So the architecture is something like So, the architecture is something like we have the battery, this is connected to whatever our charger, and charger is connected to the cloud. Right. So, this is the case while we are doing the charging of the battery. The second case is we have a battery. Now, this battery is actually inside the vehicle, right. In that case, the vehicle has a unit somewhere which is actually a 2G or a 4G module, and this in turn is sending the data to the cloud. Right. So, these are the two ways that you can capture the data. If the battery is not having a directly inbuilt embedded chip of 2G or a 4G module inside. Now, we keep on talking theoretically that this is the data you should capture from the battery, from the motors and subsystems. Since we have been talking throughout this course that the batteries are the most important part of this whole EV system, and the one of the reasons being that it is that it is the costliest part in the vehicle, second also being probably this is the newest form of the fuel that we are talking about, and thirdly also because this is not very safe if it is left alone. So, you need to continuously keep on monitoring that. So, for example, for this class I am more focusing on the cell level data or the battery on the battery subsystem. So, let us look at the cell level data, what all things that we monitor and what are the things that help in analyzing the battery or the cells and different parameters that you have already studied. So, the first case that I am taking here is the SOC imbalance during driving. All of us know about the cell imbalance and how do we do the cell balancing in the battery management system. Now, we know that cell imbalance is a very crucial, can actually play a very crucial role in the damage of the battery, and this is the most common cause of damage whenever we are talking about a battery, right. So, what do we need to do is that while it is getting charged or it is getting discharged, we keep on monitoring the cell information, that what is the deviation that it is going through for any given cycle of charge discharge. So, here the case that we have taken is the SOC imbalance, the state of charge imbalance. So, while we are charging or driving the car or an EV, what is the imbalance that is happening in the SOC? While you are discharging, all the cells may not be discharged by the same level, that is the state of charge could be different. Now, what is the tolerance limit that you can actually tolerate as far as this imbalance is concerned is important to keep on monitoring. If we do not monitor and left it alone, any single cell or a pair of the cell that causes that goes through the cell imbalance would be really causing a big damage to the battery, and that is where we have to see that how do we control that. So, analysis helps in figuring out where things are wrong, and after that you need to have that control. What do you do to control the monitored damage such that the damage could be avoided as far as possible. So, here if you see there are three limits. This is the first limit which is defined in the battery pack or in the BMS. We say this is the defined limit in which the cell imbalance can happen. So, your delta percentage of the SOC could be tolerated in this limit. I mean, this is the defined limit, should be lying between this limit. All the values that fall in this range are the normal values. Certainly, when we are driving, we are not controlling any cell imbalance, and most of the time the cell balancing happens during the charging or while it is ideal. We are not able to do much of the cell balancing while the battery is getting driven, because the driving charge rate or discharge rate is not in our control or the BMS control. So, that is where monitoring becomes very important. So, we say that this is the prescribed limit, and let us say this is the tolerable limit. So, this is the tolerable limit, prescribed limit. So, if we say that if it is going beyond the prescribed limit, I define a tolerable limit that it can actually lie within this part and we need not take any action. But what if it exceeds the tolerable limit as also, right? Further we can define various levels, it could be this, and what are the actions to be taken. What if it is this, this means the cell is already damaged or it is going towards a damage, and you need to control that immediately if you want to prevent a blast in the battery, a burst of the battery, so on and so forth, or any connection has gone bad or MOSFET is not working, etc., etc. So whatever has gone bad in the battery, the user doesn't know. All the technicalities are transparent to the user, so he just understands that something has gone wrong. But how would you convey that in a simple term is that while we are monitoring all this, only then it is possible that we convey to the user in time and the operator or the OEM also in time, such that they can take a good action on it. Similar stuff when we do for the imbalance during charging, and this is for cell voltage. We just talked about the SOC percentage delta. Similar is the thing that we talk about delta voltage difference between one cell and the other cell, and we keep on monitoring that the similar ranges that we have defined for SOC, we define it for the voltage also. So now based upon the cell, their chemistry, their characteristics, these delta range could be different for every different cells, and also based upon what is the cell balancing technique that you are using, what is the BMS, what is the BMS chip that has been used. Accordingly, these values are defined. That means what would be the prescribed limit, what can be the tolerable limit, and how and when to take a call, right. So for an NMC battery or an NCA or LMO or whatever different batteries and chemistries that we have been talking about, it really depends upon that how much is the cell tolerable to this delta variation. So again we see one outlier. So this again is from one of our readings, live readings that we had been doing.
What is the vertical axis and what is the horizontal axis?
So the vertical axis, on the vertical axis it is a plot for delta voltage, and on the x-axis is the number of cells. So we are monitoring number of cells in a pack, and in that given pack what cell number or what is that cell pair number which is going into imbalance. So keep on monitoring all the cells. So a battery we know is made up of series and parallel combination of cells or the modules that we make of 2p or 4p, etc., and that single module is getting monitored in that whole pack, and we keep on monitoring that. Two things to do: one, to take a call what to do if it is an outlier; second, how much of it we should keep on balancing, and if we find something critical, what is the action to be taken? Is it that within that tolerable limit, if we start charging it slowly and keep it for a longer time, then probably the balancing would happen and it would be a good pack to be used again. So that is one part. Another could be that no, it has actually gone bad and you cannot use that. But unless we have such monitoring in place, we cannot figure that out. And for this kind of fuel, when we say that the batteries are nothing but like the high energy density is one that we start talking about, these are actually the bombs, and you need to control and see that the bombs do not blast while you are driving. Similar readings for the graph, again we are monitoring the delta voltages for every cell in the battery pack and seeing that what is the cell imbalance that is happening with respect to their voltage levels, that is their charge levels or discharge levels. Now this particular graph is for the driving, just as a sample. Now as we know that, as we talk about how much is the voltage, what is the SOC that the cells are or the batteries are getting charged or discharged while driving, charged while charging, the crucial another crucial parameter is the temperature. And in the previous classes, Professor had also talked about the impact of temperature on the battery performance, right. So we know that monitoring the temperature is very, very important. We try to maintain the temperature of a battery and keep it under some limits. Dr. Kaushal had also taught about how do we do thermal management of batteries and why it is important. So we know that what is the importance of maintaining that temperature, but what if the temperatures are not being maintained? So either it is not being maintained in the lower limit or it is surpassing the upper limit. What do we do? that is one question, that what do we do, but we come to that only when we know that this has happened. That means again the analytics becomes important. So this graph is for showing the duration in which the battery is spending the time at that particular temperature while driving. Similarly, we will have graphs for charging. So here if you see, this is across the batteries. So for example, if there is an operator who is using n number of batteries, this plot you would see that is for about 23 batteries. So we are monitoring 23 batteries continuously and seeing that for how long each of the battery is spending time and what temperature. Now for these colors, I mean you can see it on your right side, the red and the orange one are at a temperature 42 degrees, and red actually shows greater than 42 degrees. So what we are trying to maintain is a temperature around 40, 42 and should not be exceeding that. But we see that some of the batteries are exceeding that temperature, right, and we have to see that what is the time that they are spending in that temperature. And if these batteries further are being used at the same place, that is in same ambient, but some are continuously being used while their operating temperature has been 30-35, while the others are showing that in that same ambient temperature and the same driving characteristics, if it is matching, they reach or surpass 42 degrees or maybe sometimes 50 degrees, 60 degrees, that means something wrong in that battery, or its thermal management is not working properly, or something has gone bad in that battery, right. So from this whole graph we can do a lot of comparison between the batteries and see that how do we filter out good batteries from the bad batteries. And if you see the pink one, that indicates that the batteries have gone into a lower temperature range. So there is a range of operation. If we are specifying that it should be 20 degrees to let us say 40 degrees, then again we have to find out the outliers, and when we find out the outliers, correlate that with the other battery performing data that we have captured and analyze the reasons around that. So again another kind of a graph where pictorially what we are showing is the temperature versus the charging data points. So while the battery is getting charged, what is the temperature that it is going to? So in the charge again, if we have specified that the temperature range should be between 20 degrees to 35 degrees, or it can reach up to 40 degrees, what is it that it is spending time at, and for how much duration it is spending time. And the way that we are capturing this data or monitoring this data is through the temperature sensors. So we have different sensors in the battery, we keep on noting that value and the battery keeps on relaying it. Now relaying again, like we talked about, either directly or indirectly it is sending us the data. Now as soon as we see that temperature of the battery inside is going higher, again then we have to take a call based upon what is the region in which it is lying. And the region of criticality depends upon a number of parameters, like not only in the battery temperature. Of course, if it is reaching 70 degrees, 80 degrees, 90 degrees, we just need to cut it off. We cannot drive in that condition, or we cannot keep on charging in that condition. Now this threshold again depends upon the chemistry of the battery. Based upon the chemistry of the battery, what is the tolerable limit that has been assigned in the BMS, and if the BMS is not working. Now reasons why temperature is going high could be anything. One of the reasons could be that BMS is not working properly, that is why it is not maintaining the temperature, or anything else, whatever has gone bad. That means if BMS is not taking a call, and if you have a server, can you control it through the server and cut off the battery and say that the battery should not be used while you are driving, or while you are charging, the charger should stop that. Okay. So whenever we say that indirect methods, while we talk about controlling or taking actions, the very basic thing is you should not compromise with the safety of the battery that has been basically defined by the BMS. So there are some parameters that have been defined by the BMS. So those are the basic prime safety features that have been defined in the BMS. Over and above that, what you can do based upon this data is what we have to decide. So BMS is there, it should be cutting off the battery, but now we are seeing it is not cutting the battery, it should be cutting off the battery. We see that there is a large risk that can happen and something can go wrong in the battery. That is where this analytics helps in controlling those kinds of things. So two ways of doing it. One, like I said, that direct. If the batteries have the 2G, 4G feature inbuilt into this, that becomes a live data monitoring. If it doesn't have, then we have certain live parameters that you can define that the battery keeps on sending you while it is getting driven. So whatever information you can retrieve and what we can do with that data is what we have to see here. Or else if we do not have anything, like battery vehicle is also not capturing the data and it is not relaying to the cloud, then if the battery also doesn't have a 2G, 4G module inside to keep on relaying that data live, then what we can do is that it keeps on storing that data into its drive, into its BMS, and while we put that battery into a charger, the charger gets that data and sends to the cloud. So if you do not get the data live, we store the data and then that data is pushed to the cloud. Along with this charging data, we also get the driving data logs, and then we perform the analytics. But in that case, you cannot control the batteries while the batteries were getting driven, right? So whatever technique we use, we have to, as far as possible, maximize what we can do while the battery is in use, or based upon what was the previous cycle, and accordingly how to take a call for the next charging cycle. So if the battery was not monitored live during the charging, what actions we can take and say that this battery should be operated in such and such way.
Since there is going to be data pulled out from battery by the charger, is the interface between the battery and the charger has to be standardized? And what kind of standardizations exist today or is possible?
Okay. When we say that data has to be extracted, the standardization becomes important part of it, because we want that wherever our vehicle is going, we are able to fetch that data through the charger, let's say. So we are talking here the charging side of it. Now if it is a public charger, there are a few standards that we have talked about. So it could be CCS, GB/T and CHAdeMO, but further depends upon how much is the parameter definition, depth or the resolution that has been defined by that protocol. As far as this protocol is telling us that you can fetch that data, we can keep that data in our cloud and store that. But if it is the battery, the direct way of it, usually they do not follow any protocol, and these are largely proprietary protocols that are put into the battery by their OEMs, and they keep on sending the data to the cloud and keep on doing their data analytics and send the reports to the users. However, the third application that we can take here is a swapping application, right, where the standardization become further very important for the sake of the interoperability that you need to have within the battery and the subsystem, even when we talk about single operator. Now there, the operator defined protocol or whatever nation has defined that protocol needs to be followed to capture that data if we want uniformity in the data. You want something else on this?
As far as I know, the standard charging protocols do not have standards for data extraction. You are talking about data extraction protocol, not charging protocol. They have charging protocols standardized, data extraction protocols are not standardized.
There is no protocol as far as data extraction is concerned. So data extraction are data extraction techniques that we use for let's say in all our computer science backgrounds, people would understand that. But when we talk about getting that data, so when we are getting that data and we are saying that we are getting through the charger, there are protocols or the standard defined between the charger and the battery. So in what format the battery would be sending that data. There are some mandatory fields like voltage, current and the temperature that it needs to keep on fetching the data while charging. So, when we say that the battery is sending that data through the charger within a described or a prescribed set of rules or the protocol that we are talking about, this is precisely the data that the battery keeps on sending during the charge. So, it is only the charge data. We cannot send through that protocol the dump of the data. So, there is no driving dump that is stored on that data which could be sent upon that, unless we build another messaging structure. I mean, we can follow the same structure of that particular protocol, but define another message through which we can send that data and pass it on to the cloud.